Here you go.
Welcome to the HPC Best Practices webinar series. The series is brought to you by the IDEAS Productivity Project with funds from the Exascale Computing Project. The series is a collaboration involving the United States Department of Energy, computing facilities at the Argonne Oak Ridge and Lawrence Berkeley National Labs. I'm Mosley Marcus from Lawrence Berkeley. Ashley from Oak Ridge and I will be the hosts for today's webinar, Introduction to Kokkos, or the Kokkos Ecosystem. And the webinar will be presented by Christian Trott from Sandia National Labs. Christian is a high-performance computing expert designing and implementing software for modern HPC systems. He, as I said, works at the Sandia National Labs, where he leads the Kokkos core team developing the performance portability program model for C++, and heads Sandia's delegation to the C++ Standards Committee. Christian serves as an advisor to numerous application teams and help the teams redesign their codes using Kokkos to achieve performance portability for the next generation of supercomputers. We have sold more than 200 tickets for this webinar, and all attendees have been muted. We will be receiving questions through the WebEx chat and also the Google Doc that you can see the link on the screen. And the webinar will have breaks so the speaker, Christian, can respond to the questions that come in. With that, Christian, please. Ashley, you give him the screen. Thank you.
Okay. Try this. So everybody can hear me? Good. So I'm going to talk about the Kokkos ecosystem. This will be partly an introduction of, what we're about. So this is something, if you heard tons of talks of me, probably the first half or so of this will be fairly familiar to you. And then I'll talk a little bit about, what our plans are for the new upcoming Exascale machines and what we are going to do going forward in terms of new things, we are developing for Kokkos. Obviously, if you attended the Kokkos session at the ECP meeting just a couple weeks ago, then a lot of that will also be not completely new to you. Okay, so why do we care about, Kokkos or something like that? The reason is that, coding is actually a pretty expensive exercise. There's this estimate that, a professional developer a software developer can write about 10 lines of code per hour. So about 20,000 lines of code per year. And this is, something coming out of like Google and Microsoft and, all these industry folks. And, it means somebody who doesn't do anything else than coding, right? He doesn't write any reports, right? You don't go to any ECP meetings or something like that, right? You don't write any papers. The only thing you do is you code. Now, a very optimistic estimate, you need to touch about 10% of your application if you want to switch the programming model. Say you go from, CUDA to one API or something like that. And that's probably an optimistic estimate. Considering that most of our apps, are somewhere between 300,000 and 600,000 lines for the big apps, then, it would take you about 2.5 man-years, just coding to switch over. And if you go to some of the larger scientific libraries, for example, like Trillinos, that escalates quite soon. Now, the problem on top of that is that we have all these different machines under there, and all of these guys now want their own kind of programming model, right? In particular, the new Exascale machines. And instead of now everybody doing that effort, for every one of these machines, the idea is that everybody writes to Kokkos, and then Kokkos maps that stuff to the underlying architectures. So what is Kokkos? Kokkos is a couple of things. It is a C++ programming model for performance portability, most and foremost. It's implemented as a template library, so it's written in C++. It sits on top of things like CUDA and OpenMP, and now starting one API and HIP, etc. One of the core features of the programming model is that it aims to be descriptive, not prescriptive. So generally, you're going to tell us, what you're trying to do, and we try to figure out, what kind of mechanisms exist on the hardware you're compiling for to, get you the best result. And another big point is that we are trying to align with the developments in the C++ standard. The Kokkos team had at the last two meetings something like 7 or 8 people who are involved in the Kokkos development. So that puts us just one step behind NVIDIA and Bloomberg in terms of being the biggest contingent at the C++ committee. Besides the programming model, Kokkos is also this expounding solution for stuff you need for science and engineering codes. It's not enough to just have a programming model. At some point you're going to ask, oh, how I want to call a matrix multiplier or sparse matrix vector multiplier or something like that. I want to build a solver. How do I do that, right? Do I have to write everything on my own? And no, the answer is you don't, because we have already math libraries based on Kokkos, which are available to you. And the other thing you're going to need is, you're going to need things like debuggers, profiling, etc., and potentially tools which actually know about Kokkos. And that's what the Kokkos-Tools project is about. Kokkos itself, all of these parts are open source. It's maintained in the github.com Kokkos organization. And we have tons and tons of users from all kinds of places. So in the ecosystem, there is numerous parts. So the core part is this programming model, right, with parallel execution and parallel data structure. On top of that, we have Kokkos Kernels, which is linear algebra kernels and also graph kernels and stuff like that. And then we have Kokkos-Tools, which provide like debugging, profiling, and in the future now tuning. And then we have this other side of a project where we have explicit funding for Kokkos support, which develops like documentation, tutorials, boot camps, and stuff like that. A couple of new things coming in is remote spaces that will give you kind of the equivalent of global arrays, as well as potentially I/O via Kokkos views. And then from the Los Alamos side, we have the Kokkos Fortran interoperability library, which is kind of cool. And if you want to know more about that, then contact us later. The Kokkos development team has been growing quite a bit, in particular in the last half year or so. We have now core developers at 5 or 6 of the 5 of the big national labs at Los Alamos, Sandia, Argonne, Oak Ridge, and Berkeley, as well as some contributors at the Swiss Supercomputing Center. And there's about 16, 17 people who are contributing to the core library right now. There's another 6, 7 who contribute to kernels, and then some people to tools and for support. Okay, are there any questions so far? I don't know, it's there.
Yes, Christian, one just came in here. Is the PGAS space available for experimentation?
Yeah, it is. Currently, it's still in the private repo on GitHub. We can give access to that. It's in very early stages. We are trying to probably make it public as an experimental capability in the next 6 weeks or so. Okay.
Thank you.
So on the core programming model, the heart of what Kokkos is these abstractions. And there are 2 sets of abstractions here. One is for data structures and one is for parallel execution. The parallel execution abstractions, that's kind of what you have in most of these programming models, right? You have things like execution spaces, like a way of saying, oh, this should execute on the GPU, this should execute on the CPU, etc. You have execution patterns, essentially the kind of structure you give your code, like a parallel loop, a parallel reduction, a scan, task graphs and stuff like that. And then there's the execution policies, which essentially control how you execute these patterns. There's things like in Kokkos, things like the range and the team policy or task graph, etc. Other things which go in there are things like, do you do dynamic scheduling or static scheduling, etc. And that's something, if you squint, you can see that in CUDA and OpenMP and stuff like that. What's a bit more elaborate on the Kokkos side is the data structure thing. On one hand, there's the memory spaces. And in Kokkos, memory spaces are, not just like host and device, but in principle, they are kind of any kind of memory space, and you can have multiple of these guys in any given hardware. And it also encodes certain semantics of the memory space. So for example, the unified memory space on NVIDIA platforms is a different memory space than the one where you just allocate on the GPU and it's not accessible to the CPU. An innovation in Kokkos was the memory layouts. And that is essentially the recognition that data access patterns are key to get, performance portability, but that data access patterns have to be different on different architectures. And that's where the memory layouts come in. So in our data structures, which are templated on the memory layouts, you essentially just by changing the type def, you can change how your logical, your algorithmic indexing maps to linear memory addresses. And that allows you to change the access patterns of your algorithms just by changing type defs instead of rewriting your whole code. A last thing there is the memory traits, and that is something you can attach to these data structures, and that expresses things like you want atomic access, you want like a restrict access, and other kind of special kind of data access paths in the hardware. So how do these core capabilities kind of look like? This is just a really tiny overview of what's in there. The first most simple thing would be something like a parallel 4. You just give it a number of iterations. You give it a loop body via a lambda, via C++ lambda, and then it will execute. And it will execute on the default execution space, with kind of all things defaulted. There's parallel reductions. You can just put there a parallel reduction, and you need to tell it, at the end of the parallel reduction as the last argument, what kind of reduction operation you want. In this case, as the example I have here, also, I can't highlight, oopsie. Also put explicitly a range policy in there. With range policy, execution space 0n is essentially the same as just giving an n if you had, if exec space is actually the default execution space. But by putting there something else, for example, saying I want the default host execution space, you can control where this thing executes. There's tightly nested loops. That's in particular important for things like structured grids, where you can. It's essentially the equivalent of an OpenMP collapse, where you say, I have like 3 or 4 or 5 or whatever many tightly nested loops, and the loop body will just get the 3 indices. It allows tiling. So in this case, I gave it the 3 start indices, 0, 0, 0, the lengths in each dimension, and 1 and 2 and 3, and also tiling information about, how big to make tiles. A really important thing for a lot of our apps is non-tightly nested loops. So if you don't have, if you have code in between these loop nestings, you still want to parallelize, multiple of these loops, because you may not have enough parallelism on the outer, on just one loop level. And that's what the tightly nested loops are for. And basically, they work the exact same way as the outer stuff. You just use different policies. Whereas task graphs, I'm not talking too much about there. The data allocation there, that's our Kokkos view with layouts and the memory spaces, etc. Data management is generally explicit, so you do deep copies explicitly. You can do atomics. You can do atomics on even arbitrary types, so you can do it on like complex double and stuff like that on all the architectures. And then there's the different execution spaces. There's tons of other capabilities I'm not going to go into. What I'm going to do is I'm going to go through a simple example of a conjugent gradient solver, as to give you a look and feel of how it looks like to write Kokkos code. And we start with something which is kind of which is coming out of mini-FE. So there's essentially just 3 math operations in this thing. There's a vector addition, a dot product, and the sparse matrix vector multiply. But before we go there, the first thing we need to do is we need to do like our data management, right? And the way this works in this case is that say you get your original data from outside, you can actually wrap that, right? So X in could be like a double star point, just a double star pointer. And you can wrap that. You say explicitly this is on host space because the data you got from somewhere else in your app was probably, allocated just with new or malloc or whatever. And the unmanaged says, I'm not going to own this data. I'm not going to free this data, because you just handed me a pointer. When I allocate a view in the default memory space, which then depends on whether you compile for GPUs or for CPUs, where that sits. And I'll deep copy, the data in. So the first loop would be, the simple data pro loop for the AXPBY. Since it's just a data pro loop, there's nothing particular interesting going on here. We can just use like a Kokkos Pro 4. This is super easy to express in most programming models. The one which is probably the most annoying right now is OpenMP target, because you have to do all these map clauses. This kernel is Benthos bound, so if you don't get a decent performance on any of the programming models, then something is wrong. But it should be simple enough. So serial implementation of this kernel, how you would find it in many applications, would be just an AXPBY. You give it the number of elements, you give it the 3 pointers and maybe an alpha and beta, and then you run that loop, and you just run through that. So how does that look in Kokkos? What you would do is you replace the pointers with views. In this case, I told explicitly that the x and y are const, because they are just read, not modified. And then the loop is replaced with a parallel 4. In this case, I gave it also a name, which is really useful for debugging and profiling purposes. I told it, n is the number of iterations. I gave it this Kokkos lambda that kind of just hides some nastiness in the programming model, like, for example, these host device annotations you need for CUDA. The lambda just takes an integer in, and then you essentially have the line as before. The only thing I replaced here is the brackets with like parentheses. So far, so good. I don't see any questions, so I'm going to go on. Yeah. Oh, good. So what's a bit more interesting is the dot product. So it's essentially a simple data pro loop, but it does a reduction over all the elements. So what you want is you want the Kokkos Pro reduce. Can I click that away? Oh, sorry. One of the problems with that is that is actually pretty non-trivial in CUDA due to the lack of built-in reduction support. So there isn't actually, like in CUDA, in the core programming model, anything to do that. You kind of can do that now with, or you can do that now with Thrust, though. It's also generally Benthos bound, and the serial implementation, would look relatively straightforward. You just get 2 pointers, you get an n number of iterations, you create a temporary, and you plus equal into the temporary. Now in the Kokkos implementation, you also get again 2 views. You tell it that the temporary where you want the result, and then you can call parallel reduce. I gave it, which is the loop pattern with a reduction. I gave it again a name and the number of iterations, and now the thing that changed here is the signature of the lambda. I don't just get the integer for the loop index. I also get like the thread local reduction variable there. That is something interesting. If you actually parallelize that upper loop, the serial implementation of OpenMP, the compiler will do for that. So the sum inside the loop would actually be a different variable than the sum outside of the loop, and it would be a different variable for every thread. Since you don't write a compiler which magically changes stuff for you under the hoods, we have to make you pass that thread local variable in. We allocate that on our side inside the parallel reduce, and then pass it to your lambda. Okay. Now, the most interesting one of these is the, oh, where was the question? Oh, there's a question of how does labeling the operations help me? I'm actually coming to that a little bit later when I'm coming to the tools section. Basically, we can provide that information to things like profiling and tuning and debugging tools. And I'll show an example of that later. And that's kind of super helpful because otherwise you get in the profiling tools these super weird type IDs as the names for your CUDA kernels or your loops or whatever. But I'll show an example of that later. Okay. Sparse matrix vector multiply. What you do in that operation is you loop over the rows of a matrix, and then you do a dot product of a matrix row with a vector for every one of these rows. It is an example of a non-tightly nested loop because you have to write the result of that inner dot product back to the left-hand side vector. And there's one more thing: you do random access on the X vector because you use this column index coming from the matrix to index into that vector. We'll see that here. We go over outer loop over the matrix rows. We do the inner dot product row with the X vector, and yeah, that's kind of it. Now, this version here looks obviously quite a bit more complicated. The reason that it looks so complicated is that this is actually a really good implementation of a sparse matback. And that's actually an implementation of a sparse matback which has been beating things like QSparse and MKL, on a wide range of matrices. And that is actually what we use in Trillinos, pretty much. So what's going on here? The first thing is we start team parallelism over row work sets. So what we did is we said, we figure out via some heuristic how many rows we give to each team of threads, and then each team will essentially handle one of these row work sets. Within that, we do a loop over all the rows within that row work set, and parallelize over the threads within the team. And then the last thing is we do a vector level reduction for each row, within each thread of the Kokkos team. In some sense, you can think of that as on for example KNL, you would say, oh, I'm using a team size of 4, so I give row work set to hyperthreads on the same core, in the assumption that if I have sorted my rows nicely, then consecutive rows will access kind of the same cache lines, or at least the same pages. And you parallelize over these row work sets, with the hyperthreads within the core, so that they collaborate on using the same cache. And then you use vectorization to vectorize the inner loop. On GPUs, what you would do is you would give a row work set to a CUDA block. Then you parallelize, say, with you give each row to a warp, and you use the warp level parallelism to do the innermost reduction. There's one more trick here for GPUs. By telling us that this X vector will be accessed with random access, we're enabling texture fetches here, which is kind of neat. This performance comparison is a little bit older. In particular, the OpenMP numbers, I wouldn't I wouldn't take them too seriously. On the other hand, I also didn't get better numbers out recently, so I don't know. What this does is essentially a comparison with other programming models. This is okay. I'll answer that in a second. What this does is essentially comparing different programming models, right? So we compared OpenACC with a raw CUDA with a Kokkos implementation and an OpenMP offload implementation on P100s and Power 8. And we ran two different problem sizes. So one of the problem sizes is 100 by 100 by 100, so you have 1 million rows, and the 200 by 200 by 200, which gives you 8 million rows. And if you look at that, generally Kokkos is roughly on par with, what the best model is. Sometimes it's a bit better, sometimes it's a bit worse. OpenMP has some weak points for some reason. On KNL, we kind of know where it is coming from. It's a bit weird. On the GPUs, it's basically immature compilers. And it really depends which compilers you're using. I think this was actually using the Clang mainline compiler. XL is supposed to be better usually, but XL currently doesn't compile our backends or doesn't compile all the code and crashed on this code, even on the native OpenMP code I implemented here for some reason. And then, yeah, any questions to that? No. Okay.
Well, Christian, there is a question here. Does Kokkos data structures provide a persistence layer for HDF5, parallel or serial?
So not currently, but actually there's a prototype out there. This is essentially as part of this remote memory space stuff. There's a prototype for kind of I/O stuff via HDF5, and we haven't productized that, but the idea is that it essentially is just exposed as a different memory space, and what you can then do is you can deep copy from that to a different view, and that would just copy from, also load the stuff from files into your stuff, into your data structures. But if you're interested in that, please contact me later, and I get you in contact with the people who are working on this kind of stuff.
Okay, go on. Oh, there is another one here coming in. Are OpenMP numbers for GPU or CPU?
In the above panel, it's for the GPU, so that's on the P100, and in the below panel, it's for the kernel.
Okay, go on, please.
Okay, so Kokkos Kernels, that's one of our math library which we provide. Basically, what it does is it does like BLAS and sparse and graph kernels on top of Kokkos and its view abstractions. Generally, it's scalar type agnostic. That means it works for any types which have the correct internal math operators. So if you want to do a vector add, right, you better have a plus operator defined. It's layout and memory space aware. So that means you can hand to Kokkos kernels, like host views or device views or whatever, and it will figure out how to execute that correctly. It can call vendor libraries when available. So if you give us the correct data layouts, the correct scalar types and stuff like that, and the memory spaces matches, when we will call into things like MKL and QSparse and QBLAS and stuff like that. One of the nice things about that interface is that it's generally simpler than the standard CBLAS interface. And the reason is that the views contain things like the size and stride information. So you don't have to give like half a dozen integers for all of it. You basically just provide, the views, the scaling parameters, and whether you want like the transpose arguments. One other thing we are working on, and where we have quite a bit of stuff already done, is we have interfaces to call Kokkos kernels at the team level. So if you think about this nesting level, we have interfaces where you can call it at that level. That means you can, for example, call a matrix vector multiply within a CUDA block, where the CUDA block will execute that one operation in parallel. If you think about, current architectures, a single SM on a V100, right, gives you almost 100 gigaflops a second in, in throughput or double precision throughput. So that's already quite a bit of stuff, right? And then it can go up to 2,000 byte parallelism. So, each of these individual ones is already a pretty hefty block, and that means in a lot of situations we can, assign like work sets or work items to one of these things, but then need to do things like solvers in that. Kokkos-Tools is essentially our tool set, which provides things like profiling and auto-tuning and debugging and stuff like that. The one which we have the most or the longest is the profiling stuff. There's new tools coming out all the time. and we work with vendors to make these tools more useful. Oh wait, there's more questions on the previous stuff. Let me go back for that.
Yes, I was going to read them for you. But
I have it open here, so I can do it.
Okay, go, yeah.
Okay. Yeah, so the 15, that was probably last summer, I would guess. So the numbers are probably better now. The Clang numbers are still horrible. So I actually try to reproduce this stuff with like just pure Clang, and the dot product is still like amazingly bad. The first time I ran that, I thought like, oh, everything is fine. It's like, 9 point something versus 10 point something, until I noticed that the units in Kokkos were microsecond, and in the raw OpenMP implementation it was milliseconds. But XL is supposed to be better, so that's why I said, I wouldn't trust these numbers too much right now. The other thing, does Kokkos insert OMP SIMD when using a thread vector range? It doesn't introduce OMP SIMD. It does add like a pragma IVDEP. And the reason that we do that is that tons of our code actually gets slower when we put OMP SIMD in there, because the problem is that most compilers right now interpret OMP SIMD. You shall vectorize that no matter what your cost model says. And in particular on KNL, we ran into tons of trouble with that, because it would inject, arbitrary bad code with like gathers and scatters, and it would actually be better to execute that in serial. So that's why we have IVDEP right now in there. We are considering changing that to pragma OMP SIMD, in particular on some of the newer hardware where we haven't seen the problems being that pronounced, and so yeah, it's a bit tough. Okay, and the last question here. It appears that Kokkos kernels are based around fixed-size matrices. No. Kokkos view double star star is 2 runtime dimensions. Right? That's not fixed size. If you had like a Kokkos view double star 5, that would be 1 runtime dimension and 1 compile time dimension. And if you do something like Kokkos view double 5 5, that would be all compile time dimensions. So the interface is doing runtime dimensions, or actually, what?
Yeah, there's a question coming in, and the speaker's waiting for
element type. No, it's not right. The Kokkos kernels with the different element types, it can take any element types. As we even like instantiate Kokkos kernels with stuff like automatic differentiation types, UQ types, and stuff like that, and other things like that. Okay, or we can come back to that. So when we said that Kokkos kernels is memory space aware, the memory space awareness is essentially it recognizes what your views are, right? You allocate the stuff in HBM or whatever you want, and then Kokkos kernels will execute in the execution space, which is the most appropriate execution space for the memory space you chose. So it's not that it internally will do, hidden deep copies, but it will, honor whatever you chose to do. Okay, I'm going to go on now with the tools.
Yes, please.
The auto-tuning is something which is under development. Essentially, it will do things like tune the internal variables, such as CUDA block size, etc. But we will also provide an interface so that you can provide variables and register with them with the kernel. You can say something like, oh, here's my tiling parameter or whatever my internal parameter, and please associate with the next kernel and give me a tuned variable back, something like that. It will do the same as profiling that means you can use those tools on your release executables. The way this works is that we deal open these tools and then essentially fill things like function pointers based on whether you loaded something. And the overhead of having this capability in your release executables is something like a pointer comparison. So it's super cheap and shouldn't, per like kernel launch or something like that. So it shouldn't really be a problem. Debugging, that's under development as well. It's essentially extensions to enable Clang debugger to use like Kokkos naming information. So you would, for example, not get a message, or you had a segfault at this pointer address, but it would also tell you, oh, this pointer address was previously allocated in a view given this name, and the error happened in the kernel called this, whatever the name is you gave the parallel for. And then the last thing we are looking at is static analysis. Essentially, we are adding paths or patterns to Clang tidy of what you shouldn't do. And I'll have an example of that in a second. So the profiling and debugging, as I said, that's one of the big things we've been working on for a while. And there's, both a set of really basic tools we have. You just type make and you just check out the tools from GitHub. You type make, and then you can run these tools. And they give you, basic timing information about what you use in terms of memory and stuff like that. If you want to know more, go to the Kokkos github.com organization, go to Kokkos-Tools, and there's a wiki page with documentation. One of the problems we try to solve with that is that abstraction layers obfuscate profile output. So, for example, in Trininos, when we run that with nvprof, there was, no, we don't want auto updates right now. There was a situation where we, which we gave to NVIDIA as an example of what's going bad, where we had a kernel name which was like 4,000 characters long. And it turned out that we had 100 kernels where the first 500 characters are all the same. And that just comes from all this templating and all these nested template instantiations, which go into the kernel name eventually. What this allows you to do is we can use these names and pass them onto third-party tools. Here in the lower side, there's an example for vtune, where if you named your stuff and you loaded the vtune hook kind of tool, you can go to this frame view of your profile in vtune, and then what you will see is you will see something like parallel4.xb, and here's the first time you called that, the second time, the third time you called that. The lowest one is we always generate a name based on the type ID, and where you had a type ID for your lambda was essentially a lambda in main. The important part is you don't need to recompile. This uses just these runtime hooks, and it all happens via setting an environment variable. We integrated with more party tools. For example, we've been working with things like Tau and also NVVP. NVIDIA just added to their system as an end systems version a thing where these names now finally show up in their stack. And here's another example, from Tau, where it tells you, oh, there's a com update Halo region, and within that region, you had these parallel 4s with these names, and then it shows you on top of that, the OpenMP parallel regions, telling you, where these regions were coming from, with the parallel 4s and stuff like that. This is an example for the static analysis thing. So in Kokkos, you're not allowed to capture by reference technically and then modify, in this nesting scope, a variable from the outer scope. And so this Clang tidy would be able to tell you that, right? You see that here in the first example that says lambda captures modifies reference. You shouldn't do that. That's kind of the stuff we are looking for. Things which technically would compile but violate the semantics of Kokkos. Okay, so that was a bit of overview of what's part of the Kokkos ecosystem, what we are trying to achieve, and I'm going to talk a little bit now in the last 20 minutes or so here about what we've been doing with that. So one of the things is we have the Kokkos-based projects. We got about a dozen or so big codes running real analysis today. So that's stuff which runs in production on the big platforms, running with like thousands of GPUs, etc. We have, on the order of like 35 of these, 500,000 line codes being completely committed to going there, and we're actively porting, but we're not necessarily all in the state yet, to being done, and being able to run their full science that way. Whereas, a number, if you go to slightly smaller packages, right, or libraries and stuff like that, there's probably like 65, maybe a bit more. And if you count, all the people who do stuff, with Kokkos, right, proxy apps or whatever, we're talking, somewhere around 100 to 150 packages is our estimate. It might be a bit low. In the end, we had about probably 500, 600 people going through at least the 2-day tutorial on Kokkos so far. So, if you divide that by typical team sizes per team, you probably end up somewhere in that order. There's tons of users on all kinds of places, both here in the US and outside. Here's an example for LAMPS, which was one of the earliest codes which was adopting Kokkos. And what you get here is you get, roughly what you expect in terms of performance. One interesting thing is that the Kokkos version of LAMPS is actually a bit faster than the vanilla version, as the original code of LAMPS. That is a thing we've seen numerous times, partly because Kokkos is a restrictive programming model. It doesn't actually allow you to do all kinds of stuff. And it turns out if you are prevented from reallocating or your data structures in the middle of your loops, then your code will be faster as a result. With the Sparta, that's also a production simulation at scale. It's a stochastic parallel verified gasp time accurate analyzer. Essentially, it's a DSMC code, the direct simulation Monte Carlo code. This is actually, to the best of my knowledge, the only code which ever ran on Trinity using both partitions, the KNL and the Haswell partition at the same time for one big MPI job. So they ran a 20,000 node MPI job on there. It was also benchmarked on Sierra with up to 16,000 GPUs and runs in production at about 5,000 GPUs. And for this was one of the codes last year which was using up the most cycles on Sierra apparently. UINTA is a framework, a system-wide tasking framework, which comes from the University of Utah, and they do some codes where, in particular, regarding like combustion and radiation simulations. They had a code which already was working on GPUs and CPUs, and then they started switching over into Kokkos. And what happened there is the same as in some sense as in LAMPS, just more pronounced. Even the CPU code got over 2x faster through this effort, and the GPU code later was also faster, and that all with one shared code base right now instead of having two code bases. Okay, so a lot of you guys are probably interested in what are we doing with the Exascale machines. So we fully released have like 3 machines, 3 kind of Exascale class architectures. All of them are Cray. At Argonne, we are getting the Intel Xeon with Intel Xe compute accelerators. Or at Oak Ridge, we get AMD CPUs with AMD GPUs. And at NERSC, with Perlmutter, we're going to get AMD CPUs with NVIDIA GPUs. And then there's another Cray for El Capitan at Lawrence Livermore, where the internals are still unreleased. So we've been thinking about this for a long time. One of the things is as I said earlier, we extended the Kokkos project to have actual developers at the other labs. So we have 1.5 FTEs both at Argonne and at Oak Ridge in terms of just development resources. We've been working on the HIP backend for AMD with the main development for it happening at Oak Ridge. We're working on the SYCL or One API thing for Intel with led by Argon. And then we are also doing OpenMP targets for all of them, which we lead at our side. And obviously, for NVIDIA, the CUDA backend is still available. So for the OpenMP target backend, the first compiler, the compiler we are getting best mileage out right now is essentially the Clang mainline compiler. That's the only compiler we kind of officially support right now. It can actually compile all the stuff we implemented so far. Every other one of these compilers currently ICEs on us, as it has internal compiler errors, which we report back. That includes IBM Excel. And we are working with those guys, on fixing it. Interestingly enough, that is even true for the AMD AOMP compiler, even though that should just be like a modified version of the Clang mainline. We're not quite sure why that fails. As said, we are testing that right now, and we have like the basic capabilities kind of working, but the performance is pretty spotty. The HIP backend, that's actually like a restart of the work we've been doing for a long time already. We actually had a complete backend for AMD working January last year, based on a different programming model they had, which was kind of C++ AMP based. And we had it working on, we started working on it something like 4 years ago. And we finally had everything working, all our internal unit tests were working, and then they told us in March that they would deprecate the programming model and throw it away, and we would need to start over. So we started over. As said, that's work led by Oak Ridge. We have, a number of our basic capabilities are in place right now. More are coming like every week. Performance is still kind of a bit funky in some places, but not as bad as with like OpenMP. So the dot product, for example, is reasonably good. Kind of where you would expect it. The vector add here in this case is slower than we would expect. So the MI60 actually has more bandwidth than the V100. But it was confirmed to us by the AMD that they see the exact same problem with just normal, standard HIP code, also even without Kokkos in the way. And we are investigating, what's going on there, why we can't get for, a simple vector add the performance they should get. The worst thing right now is the one API backend. The biggest problem there is the tools. We are working basically not on pure SYCL, because pure SYCL cannot implement Kokkos. It also can't implement like C++ 17 algorithms or anything like that. So it's DP++ we are using. There's all kinds of extensions we essentially need, and we're going to use all of them. There's weird bugs in the driver. For example, the driver for the current test platform thought that all the pointers on my GPU, on my little embedded GPU, are 32-bit. So it essentially threw away 32 bits of our pointers we captured in lambdas, which was kind of weird. So we'll see where it goes. We have a couple of capabilities working, but it's pretty spotty at this point. Okay. Last thing I want to talk about is the Kokkos C++ standard integration cycle. So essentially, I said we are working a lot on the C++ standard. And what we are trying to do there is we are trying to get features from Kokkos into the C++ standard. Oh, just for a second, no, there was no new question, so I'm gonna go on.
There's a question there right now.
Oh, yeah. So the OpenMP target backend, in principle, it should, as the current OpenMP backend is not, because it's OpenMP free, so it only works on CPUs. The OpenMP target backend will, in principle, be portable. We are pretty committed to doing that, as that it will work across all of them. Essentially, we want a second tool chain available on every one of these platforms. But the reason that, right now essentially only Clang works, all the other compilers crash internally when compiling our test framework. So, what can we do? We essentially just report bugs back to the compiler vendors and tell them, here's the reproducer, fix it. And we are trying to fix it. And we'll see how it goes. Okay, back to the C++ standard.
Yes.
Essentially what we do is we propose new features for the C++ standard. What we then do is we actually implement these features when they get accepted in a backport to C++ standards we can actually use. So for example, things we proposed for C++ 23, we actually have versions which work with C++ 11. And what we then will do is we essentially port the accepted features, as we take our legacy implementation of that and just implement it as a thin wrapper around the new version of these capabilities. And what that allows us to do is if you then happen to have a compiler which has that feature already built in, then you can just switch our implementation out for the compiler implementation underneath, and everything is fine. There's a couple of things in works. One of them was the first success was atomic rest. That's actually in C++ 20, and that provides atomics with all the capabilities we have for atomics in Kokkos. So you can just reference like a non-atomic allocation and then do atomic operations on top of that. And that even works for things which are not natively supported in the hardware, even for arbitrary sizes. So things like, atomics on stud complex, for example, should work. The next thing we're working on is Kokkos View for std span. That essentially gives you those multidimensional arrays with layouts and everything on all these other things. It's pretty cool. We can basically do anything in there we could do with Kokkos Views, but the design is much better, so it will be easier to write your custom layouts. Also, it's arbitrary rank, so it's not just rank 8 like in Kokkos Views. You can actually make it arbitrary rank, until your compiler crashes because of inline def or something like that. And we're hoping right now that we land that early in the cycle for C++ 23, potentially at the next meeting. There's a production reference implementation available of that thing in the Kokkos organization. The other thing here is what we're working for is we work on executors. That's the parallel execution in C++, and then basic linear algebra. That is actually a really cool proposal. We are really proud of that. And it will support like mixed precision. It will support layout awareness. It will support things like batched linear algebra, etc. Okay, last thing before I'm done here, features which are currently in the works or just made it into 3.0 is in 3.0 is the full CMake build system with potentially also with like spec. The spec stuff is something we're still working on, but the pure CMake, with modern CMake kind of works now. So you do find package Kokkos, you add your library, and then you say target link libraries, or you add your executable and do like target link libraries and just point to Kokkos and everything is fine. We have SIMD types coming up. That's in the Kokkos organization under SIMD Math right now, but we're going to move that into Kokkos Core relatively soon. That's an experimental capability, but that will give you portable SIMD types even for GPUs. We're working on things like CUDA graph support, then these resilience and remote spaces, and another thing which is coming is because we had a couple applications asking for this, we wanted memory pools, and we're going to put like Livermore's umpire library underneath some of our memory spaces. Oh, the std blast is still private. Yeah, I might not have clicked it public yet. I'll click it public later this week. Okay. Here's more information. So you can go to github.com/Kokkos. There's all the repositories. You can find all kinds of talks. Even if you go to YouTube and look for Kokkos, you find all kinds of talks, recorded talks from us. And then if you have questions, join our Slack channel, kokkosteam.slack.com. If you have registered with Slack with your DOE address, like National Lab address or something like that, then you should be able to just join. Those are all whitelisted. And with that, I'm pretty much done, and we have like 5 minutes left for questions.
There is one coming in right now. Can you read that question, or please? Christian.
Oh, yeah. Okay, can someone outside the listed organizations join the Slack channel? In principle, yes, but we can also add, so I've also been adding new organizations where, like in particular universities, I usually just add the university domain to it. Can Kokkos be used for porting existing applications implemented in C++ and also in Fortran? That is what we are doing, right? The number of applications which are written from scratch new in Kokkos is super low. It's almost always, porting existing applications, and often also with like Fortran stuff. In particular, Los Alamos has been doing that a lot, and we have this interoperability library which allows you to like see Fortran allocations in C++ as Kokkos views and vice versa and stuff like that to make that easier. How does the integration of the Umpire library looks like in Kokkos? We have some prototype stuff internally for this already. Basically, it will be exposed as its own memory space. In fact, it will be exposed as like a templated memory space, like how the Umpire has these different kinds of, allocators and stuff like that. So there will be essentially an Umpire memory space templated on the kind of allocator type from Umpire you want to use. Does Kokkos provide Mac GPU support for macOS 10.14 and higher? You mean for NVIDIA GPUs? I don't know. Are there still Macs with NVIDIA GPUs? We definitely don't have like OpenCL support or anything like that. We don't have OpenCL support because there is no C++ OpenCL really supported by anybody. And we have not tested, as we are not internally testing NVIDIA GPUs on Macs, as on older Macs. I know that some people have done that and it worked. So we'll see.
There is another question coming in.
Yeah. Is there a plan to support multi-streaming for CUDA with Kokkos? So CUDA stream support is actually already in there. What we don't support currently is multiple GPUs within the same process. But CUDA stream support is actually relatively new and that's in there. Right now, it's mostly an interoperability thing. So you still have to create the stream because we haven't yet done the generic interface to essentially kind of split devices. Okay. It is not clear to me at what level Kokkos integrates with MPI. So Kokkos integrates with MPI essentially the same way as CUDA or OpenMP integrates with MPI. That means, from some perspective, not at all. From some perspective, totally fine. So the way we do that is we would essentially just extract, pointers from contiguous views and pass these pointers to MPI operations. And, depending on whether your MPI is, for example, GPU aware or not, you need to do the deep copy, first. So you copy from like a device view to a host view, and then you pass it on. No, we don't. No, Kokkos itself doesn't support like distributed objects natively or something like that, right? You can build these things on top of it, like Trillinos builds these things on top of it, it's distributed matrices and whatnot, but Kokkos itself doesn't. What Kokkos will do, though, relatively soon is the PGAS models, right? Which means you could get like distributed allocations like global arrays. How the performance looks across the whole cluster, that's gonna be to be seen. Where it does work really well is on things like NVLink connected boxes like DGX2s. That's something where going to a complete PGAS model like global arrays actually works really well.
Okay, I think that's about it for the questions. Ashley, could you give me the presenter view, please?
Coming your way.
All right, so I'd like to share my screen here to thank you very much, everybody, for participating. Thank you, Christian, for this nice webinar. So we would like to keep improving the series, so please give us feedback through that survey, the link you have there. So the slides and recording will be available at those 2 links there next week, a week from today. I'd like to announce the next webinar that's going to be a month down the road, testing strategies when learning programming models and using high performance libraries. And that webinar is going to be presented by Balint Drew from the Jefferson Lab. And we have already the registration open for that webinar in March. Thank you all again. Do you have any final